Okay, chapter 8, the quantum mechanical model of the atom. And here's one of my favorite scientist quotes, Niels Bohr. Anyone who is not shocked by quantum mechanics has not understood it. So the stuff I'm going to present to you today is disturbing. On a scientific level, right? Not on there's nothing gross or immoral or anything like that. But it's just like, it's mentally, it's like, that's not right. That's not possible. So just be prepared. So until the beginning of the 20th century, it was believed that all physical phenomena were deterministic. What does that mean? Deterministic means that the present conditions of something determine its future behavior. So if you shoot an arrow down a path and record where it lands, and you shoot another arrow in the same way, it's going to go the same place, right? Well, a bunch of physicists were doing work with subatomic particles, and they found that the present condition does not determine the future condition for these really, really small things. And so if you shoot an electron down a path and record where it lands, and you shoot an electron down the path in exactly the same way, it's going to land somewhere else. And that just doesn't make sense based on our observations of the macroscopic world, right? That's not how things are supposed to work. And that's because an electron is absolutely small. It's in the quantum world, so smallest pieces. And these things behave differently than the large or macroscopic world that we can actually see. So, this is very disturbing, but when unobserved, absolutely small particles like electrons can be in two different states at the same time. So the electron can be a particle and it can be a wave. Or an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. And if that seems impossible, then your brain is working, okay? The scientists that came up with this stuff didn't like it, and they didn't understand it either, and I don't think anyone who has ever lived claims to completely understand how this works. It's bothersome. It's definitely bothersome. So electrons are incredibly small, and just, to help us get an idea of how small are electrons, a single speck of dust. So a speck of dust, that's like about the smallest thing you can actually see with your eyes, right? Single speck of dust has more electrons than the number of people who have ever lived on the earth all put together. Right? A couple of open mouths. Good response. Yeah, that's a lot of electrons. Billions, right? Billions and billions. And so that's in a speck of dust. So then you think about, well, like this bench top, how many electrons are in that? Just mind-boggling. But small thing, and it's got that many pieces in it, the electron is so small, you just can't even get your mind around it. The behavior of the electrons influences the behavior of the atoms. Much of the behavior of atoms is due to what the electrons are doing, and so we have to look at what are these electrons doing. Directly observing electrons is impossible because they're so small, right? And then the other problem with observing electrons is that when you observe them, their behavior changes. So this is like, one of those kids that was always behaved themselves when the teachers were around. But, when the playground supervisor was looking away, this kid was beating you in the stomach or something, right? Just nasty person. Behave differently when being observed. So electrons are kind of like that. Even shining a light on the electron affects its behavior. And I do not expect you to understand how could that be, because I have a hard time with it. So, Schrodinger's cat, you may have heard of this experiment. This was a thought experiment that is frequently misunderstood. And this thought experiment demonstrates how quantum strangeness does not transfer to the macroscopic world. he meant this to demonstrate how ridiculous the behavior of the quantum world is when applied to regular things. Regular things like a cat is a regular thing. So I've got a couple of videos here because these say it much better than I ever could. So we'll get this up here.
This wouldn't be a YouTube channel without a cat video. So
Sorry.
without further ado, we present Schrodinger's Cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So Minute Physics is a great site that, condenses things into a very short period of time. And then here's another one.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Think to say, what? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. So you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but the cat isn't a quantum object. cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws, so it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Okay, now I'm sure that some of you have some questions. Any questions? I know, right? You had some questions earlier.
I did. But I like that second video.
Yeah, I showed both of them because they kind of showed different aspects of the idea.
So, never mind, I'm not even.
Yeah. This is one of those things where it's like I have lots and lots of questions, but I can't actually formulate them into words and speak them, right?
So, I'm sure we're going to go into this, but what do you do with this?
What do you do with this?
Computer.
Well,
yeah, how do we apply
okay.
this idea?
Yeah, so we will be applying this idea. This idea helps us to understand the behavior of electrons. Because things that we observe seem to contradict. It's like, well, it acts this way, but then it acts this way, and how can it be both of those things? Well, it's because it's quantum, and it can be in two states at the same time. Yeah.
Okay, so his, I guess, theory or overall aspect of kind of know is that when you observe it at the microscopic level, they're all in different states, but when you look at it in, I guess, real world and macroscopic, it just seems constant.
So. Yeah, the thing is that even on the quantum level, if you observe it, you can't observe both states at the same time. If it's not observed, it is in both states at the same time. But when you observe it, you force it to be one thing or the other. And that's what really is mind-blowing. Okay. How does it know it's being observed? Will this be on the test? There will be no specific questions about Schrodinger's cat. No. But this is to get us into stuff that will be on the test.
So is a non-quantum object or like a normal object anything that has like a heartbeat, like a living thing?
A non-quantum object is anything that's large enough that you could see.
Like a tree?
A tree, yeah. Even something that is microscopic, that you could see with a microscope, is still considered a regular object, like a bacteria or something.
So is the moon a quantum object?
No. Quantum objects are extremely small, absolutely small.
Bacteria.
So how do they seem to see these quantum things to know that they...
That's an excellent question. How do we observe an electron when it's too small to see? We can only observe them indirectly. So, and that's one of the frustrating and fascinating things about science, is that we have these questions, and it's not like we can just go, you know, and outside and look. Well, what color is the sky today? Well, it's blue. I can just go out and see it. We have to infer things, and so we look at behavior caused by the electrons, and we look at the effects, right? It's a little bit like the wind, right? Can you see wind? No, but you can see what the wind does to trees, right? So by looking at the trees waving around, we say, oh, well, it's windy today. You can go outside and you can feel it, but you can't see the wind. So it's a little bit like that.
But at that point, like, the wind is observable. We can see what it's doing.
Right.
It says that you can't even observe.
Well, the thing is, we can observe the effects of an electron, but when we observe it, we force it to behave either like a particle or like a wave. When it's not observed, it's both at the same time. It's very, very disturbing.
So how do they know that it's both at the same time if it's not able to use it?
That is an excellent question. How do we know it's both at the same time if it's not able to be observed? When we observe it one way, it becomes a particle. When we observe it a different way, it becomes a wave.
So is this even real? Like, you know?
So this is, yeah, so is this even real? Okay, so here at the bottom, Albert Einstein did not like quantum mechanics. He attempted unsuccessfully to disprove it until he died. So Einstein, right? Everybody knows who Einstein was, right? Great scientist. Einstein didn't like it. Einstein set out and was like, I don't like this. I'm going to prove that this is wrong. Couldn't do it.
Well, did the Schrödinger prove that it was right?
You can't prove that anything's right. You can't prove that anything is right. You can prove something wrong, but you can't prove it to be right, because some of the things that we've thought were correct in the past were correct as far as our knowledge went. But then when we develop microscopes and we can look and see smaller things, then we realize, oh, that wasn't quite correct.
So the reason we're even studying this is because no one has proved that it's wrong.
Correct. It is the currently accepted theory.
Okay.
And the closest thing to truth we can come to in science is theory that cannot be disproved so far. Yeah. Good questions. Yeah.
Is this the same thing that saying if a tree falls down in the middle of the forest and you don't hear it, does it make sound? Because like if you can't observe it, you don't know. There's like
So that's really a slight. It's a similar question. If a tree falls in the forest and there's no one to hear it, does it make a sound? That's a similar kind of question, but it is not related to quantum mechanics. So there's that quote from Bohr again, and Schrödinger, the guy of Schrdingers Cat, said, I don't like it, and I'm sorry I ever had anything to do with it. Right? So this stuff is strange. It's disturbing. It just doesn't make sense because it doesn't match up with our everyday experiences at all. Right? So it's just disturbing. But it does explain how electrons exist and behave in atoms, and it helps us to understand and predict properties of atoms that are directly related to the electrons. It helps us to understand why are some elements metals and some are nonmetals. Why do some elements gain 1 electron when they form an anion? Why do others gain 2 electrons? Why does phosphorus gain 3 electrons when it forms an anion? Quantum mechanics explains this. Why are some elements very reactive, others are practically inert? And it also helps us to understand periodic properties of the elements.